We defined the direction of a magnetic field in two ways. What was one of the ways that we defined the direction of the magnetic field? Anyone? Just say it. If you have the answer, just say it. Towards the south. So there's two ways. The second way we defined it is away from north and towards south, although I don't really care what order you give them to me. That means if you've got a bar magnet that looks like this with a south pole and a north pole, the magnetic field is going to go away from the north and toward the south. If you have a magnetic field that's drawn like this with no magnets, you know that it's got to be caused by either a north pole over here or a south pole over here, or some sort of combination of both of those. Joel, question? No? Oh, you have the other one? Okay, good. Joel, what's the other one? Good, the way that a compass needle points when placed in the magnetic field. When we talk about the compass needle, there's two ends to the compass needle, of course, right? Compass needle is just a magnet. It's got a north pole and a south pole. So when we talk about the way that a compass needle points when placed in the field, we're really talking about the north pole of the compass. Because, of course, if the magnetic field points the way that the north pole points, then it's going to be away from the north, and it's going to be toward the south. The north pole of a compass is going to be attracted toward the south. Now that leaves us with what seems to be a bit of a contradiction. We talk about the Earth's magnetic field, a magnetic field that looks like the magnetic field surrounding a bar magnet, but really is the magnetic field surrounding the Earth. Let's pretend there's a little bar magnet inside the Earth. That means that the magnetic field has to be such that the south pole is way up in Canada somewhere or near Canada. And the north pole, magnetically that is, the magnetic south pole and the magnetic north pole are reversed according to what we normally think of them as, according to geographic north and geographic south. We also talked yesterday about a guy named Hans Christian Ørsted. He discovered probably the biggest single discovery in technology ever, and that is that moving charges, or an electric current, and that's really all an electric current is moving charges. Moving charges, electric currents, generate a magnetic field. Every single time, moving charges generate a magnetic field. Now, we can determine the shape of that magnetic field. We can determine the direction of that magnetic field fairly easily, although it's not quite as easy as just memorizing a diagram like those bar magnet diagrams that we had. I get an electron going, which way does that X mean, by the way? Into the page. I've got an electron going into the page. What's the shape of the magnetic field that surrounds this electron moving into the page? What's the shape of it? Don't tell me what the direction is right now. That's another question. What's the shape of it? Circle. Yeah, in fact, it's a bunch of circles, concentric circles, circles around circles. There's one magnetic field line. There's another magnetic field line, and so on. What do we notice about the spacing of these magnetic field lines yesterday? I'm sorry? They're not equal, right? They get further apart as they get further away from what causes it, the moving charged particle. That tells us the strength of the magnetic field is stronger where? Magnetic field is stronger in position A or in position B? A. Wherever you have closer field lines, then you're going to have a stronger magnetic field. And that should make some sense to us, right? If it's the moving charge that's causing the magnetic field, then of course it's going to be stronger magnetic field close to the moving charge. Now, how do we figure out what the direction of this magnetic field is? We got the shape of it. Okay, we know what it looks like. We know that it's a non-uniform field because it varies depending upon where you are. But how do we figure out what the direction of the magnetic field is? It's a vector field. It's got to have a direction. We're going to use the Wiregrass Rule, right? And the Wiregrass Rule, you might see it named something else somewhere else. It doesn't matter what it's called. Okay, what we call the Wiregrass Rule says stick your thumb somewhere and stick your fingers, bend your fingers a little bit, and stick those fingers somewhere else. The thumb, is going to go where? Which way do you stick your left thumb? No, thumb doesn't go counterclockwise. Yeah, the thumb is going to go into the page here. The thumb's going to go in the direction of the particle. The particle is moving into the page. The thumb goes into the page. By the way, why are we using our left thumb here as opposed to our right thumb? It's a negative charge. We're going to use our right thumb if it's a positive charge, like an alpha particle or whatever. That's a really good thing, a really important thing to take note of when you're reading a question. Okay, you read that question, you see the word electron, you see the word proton, you see the word negative ion, you see the word alpha particle. Okay, circle that or highlight it or underline it or something to remind you which hand you've got to use. That's the most common mistake that people make here. They just get caught up in using the left hand, or they're having a little bit of trouble with the last question. They move on to the next question. They read it, they realize exactly what they've got to do, the Wiregrass Rule, and they just pick up their right hand and use it because they were flustered from the last question or something, okay? Really, really common mistake just to use the wrong hand. So make sure that when you see that word electron or alpha particle or whatever, draw attention to it to remind yourself which hand you've got to use. And then literally just write down LH or RH for left hand or right hand, again, to remind you which one you're going to use. So thumb goes in the direction of the particle here. Left thumb, direction of the particle, which is into the page. Fingers are going to be bent a little bit, and the fingertips are going to point in the direction of the magnetic field. That magnetic field, right now, where are my fingers? Relative to this moving charge, where are my fingertips? Are my fingertips below the wire? To the right of the wire? Where are my fingertips right now? They're above the wire, right? My fingertips above the wire are pointing to the left. Now, if I had done this somewhere else, I would have found that my fingertips below the wire are pointing to the right. It doesn't make any difference where you do it, because in the end, my fingertips are pointing counterclockwise, regardless of whether it's below the wire, above the wire, to the right of the wire, to the left of the wire, whatever. So the magnetic field in this case is going to be counterclockwise. What if we've got one like this? These ones tend to be a little bit tougher. This is also an electron current. Electrons moving through a wire down the page. We want to find, well, the shape of the magnetic field is circular, like this, around the wire, right? This is the wire. The magnetic field goes like this. But what's the direction of it? What's the direction of it right here at position A? What's the direction of it at position B? What's the direction of it in front of the wire and behind the wire? Which hand are we going to use? Left hand or right hand? We're going to use the left hand because it's an electron. It's a negative particle. So we're going to stick our thumb which way? I see a couple of people literally sticking their thumb down. Thumb is going to go down in the direction of the charged particle, the direction of the current. So it's down the page, toward the bottom of the page. Now, for these ones, it's sometimes helpful to have a little manipulative. Use your pen. Use a pencil. Use a ruler or something to represent the wire. I'm going to stick the wire down. Okay? I'm going to stick my thumb down in the direction of the current in that wire, that pretend current in my pen. I'm going to stick my fingers to the left. Okay? Your frame of reference here. Okay? It's to the left of the wire. My fingertips are to the left of the wire. If this is the plane of the page, where are my fingertips pointing? Out of the page, right? Out of the page. If this is the plane of the page, then my fingertips are pointing out of the page. So to the left of the wire, position A, the magnetic field would be out of the page. Now, turn this around a little bit. Thumb is still pointing down, but now my fingers are to the right of the page. Sorry, to the right of the wire. Which way are they pointing now? Into the page. Good. Into the page. Now, you got a couple of options for the other ones. You can just kind of trace it around and say, okay, look, if it's out of the page here and into the page here, okay, we can kind of trace it around like this and say, all right, that's to the right. When it's in front of the wire, it's to the right. And when it's behind the wire, it's to the left. You can do that. Or you can continue on using the Wiregrass Rule and say, let's put my fingertips in front of the wire. They're pointing to the right. Put my fingertips behind the wire. Got to turn your body around a little bit here. Fingertips behind the wire, they're pointing which way? Pointing to the left. Make some sense? That's where our quiz is going to be up to tomorrow, okay? What do we see up here on the board right now? What does that look like to you? Yeah, it's a speaker. It's a speaker. I told you guys there's a million, more than a million technologies. I mean, usually we use the word million to exaggerate. Okay? Not at all this time. There's just about every technology, modern technology we have, is based on the principle, at least in part, that we talked about yesterday, and that's Ørsted's discovery that electricity produces magnetism. This is another one. Okay, a speaker is just one of millions of examples of a technology that's based on that principle. How does a speaker work? When you hook up a speaker to your stereo, you hook it up with wires. What do you think goes through those wires? Sound? Sound doesn't travel through wires. So, I mean, sound can travel through metal, but it's not the sound that's going from the stereo through the wires to the speaker. If you wanted to carry the sound directly from your stereo to your speaker, then you'd probably have some kind of hollow tube as opposed to some kind of copper wire. So what's being carried from the stereo to the speaker? Electric current, electricity. So what happens here? The electric current goes through this wire. Let's do it in red here so you can see it a little bit better. Goes through this wire. Then what do you see here? The wire is wrapped around. What does that do when the electric current goes through that coil of wire? It generates a what? It makes an electromagnet. It generates a magnetic field, right? So it becomes an electromagnet. Inside that coil of wire is a permanent magnet, just a regular magnet. It's like a bar magnet, except it's not rectangular. It would probably be circular or cylindrical. That magnet now reacts to this coil that's become an electromagnet. As the current goes through this coil, it becomes magnetized. It interacts with the permanent magnet that's already there and pushes it back and forth, depending upon which way the current's going. Okay, if the current's going one way, it's going to affect the magnet inside to go one way. If the current's going the other way, it's going to affect it the other way. That magnet that goes back and forth inside pushes this cone, this felt cone, back and forth as well. What does that felt cone do? As it goes back and forth, it pushes the air back and forth. That's sound. Sound, vibrations of air is sound. So by simply having an electric current through this wire, generating a magnetic field according to what Ørsted discovered almost 200 years ago, move a magnet back and forth, okay, that moves a magnet back and forth, that moves a cone back and forth, that generates the sound that we hear. Does that make sense? It's as simple as that. It's as simple as that. How do we hear the song? Or how do we hear someone's voice? Well, it's because the current is directly related to the sound that was generated. The current is directly related to the sound that was generated. So as the current changes, it changes the magnetic field. It changes how the little magnet inside gets pushed back and forth. It changes how the cone gets pushed back and forth, and therefore it changes the sound that's generated. Does that make sense? What's this? Yeah, it's like a fire alarm. It's like it could be a doorbell. Okay, not a ding-dong doorbell, but just a bell that just keeps ringing, like ding, 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 kind of like a fire alarm. Okay, how does this work? We got a battery up here. Electrons leave the negative end of the battery. They go this way. When the switch is pressed, that is. Okay, when you press the switch, electrons will start flowing. They're going to go through this wire right here. Can't see this very well. I'm not sure if you can see it from where you're sitting or not. It goes through this make-break contact right here, goes through this little plate right here, around these coils right here, and back out around here, completes the circuit. What happens is the electricity, the electric current, the electrons go through those coils. It generates a magnetic field. So those coils that have a little iron core or a steel core inside them become magnets. So what? Well, as they become magnets, they attract this piece of steel right here. As they attract this piece of steel, this hammer gets pulled towards this bell. What do you hear? what happens? You hear a ding. That's it. That's not a doorbell. That's not a good fire alarm when it says one ding. But what happens? This contact has now been broken. This make-break contact right here has been broken. So the electric current stops. What happens to the magnetic field generated by this? Shuts off, right? There's no magnetic field. This little spring right here pulls this back, makes contact again. The electric current starts flowing again, remagnetizes these electromagnets, pulls it back, ding, breaks the circuit, spring pulls it back, completes the circuit again, remagnetizes these, attracts it, makes another ding, pulls it back, and so on and so on and so on. As long as you have your finger on the switch, then it's going to go ding, 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 and so on. Make sense? Again, a fairly simple technology, but primarily based on that discovery that was made almost 200 years ago by Hans Christian Ørsted. Let's do one more little thing with our review here, and then I'm going to give you a couple multiple choice questions to work on. We talked about those cores and those solenoids with wire wrapped around the core, wire wrapped around a piece of steel or a piece of iron or something that's ferromagnetic. How do we determine the polarity of that? We've seen from the last two applications that I just showed you that these coils become magnetic. They become electromagnets. But how would we determine the polarity of it if we needed the polarity, if we needed to know which end was north and which end was south? First of all, we have to know which way the current's going. Tell me which way the current is going in this case. Clockwise or counterclockwise? Does it leave this end or does it leave this end? First one or second one? This is positive, this is negative, leaves the negative, goes around this way. So the electric current's going to go up in the back, down in the front. Up in the back, down in the front, and so on. Okay, does that make sense so far? There's nothing magnetic about that. That's just, here's a battery. This is the way the current goes as a result of the battery. Okay, electrons flow counterclockwise. What's the polarity of this? Take that piece of paper that we used yesterday, roll it up, make your coil of wire. We know that the current is going down in the front, so the side of the paper, the side of the coil that you're looking at is the front. Put your fingers down in the front. And remember with the Wiregrass Rule, the fingers pointed in the direction of the magnetic field. Remember with the Coil Rule, it's the opposite. The fingers point in the direction of the current. So my fingers are going to point down in the front. Now, if I happen to put my fingers in the back, okay, behind it, well, my fingers should point up because the current is going up in the back. Down in the front, up in the back. Doesn't matter. Okay? Down in the front or up in the back. Got it, Nick? Okay. So let's say down in the front. Which way does my thumb happen to point when my fingers are pointing down in the front? It's pointing towards the left. So that means the magnetic field inside here, inside this coil, is to the left. What end of the magnet is this? Somebody said it. It's going to be south, and this end is going to be north. I'm sorry? What did I say? Yeah, it should be to the left. You're right. Isn't that nice? The political way to say it. She says, "Isn't that to the right?" And she knows very well it's to the right. So I'm the one that's having a little bit of trouble right now with the difference between left and right. Courtney's saying, just to be nice, she wants to correct my mistake, but not make me feel stupid. So she says, "Isn't that to the right?" You know what? Teachers become very good at this, but every once in a while, we still make a mistake on this. Sometimes you don't understand that every time I talk about left and right, okay, it's backwards. So I have to learn to say, okay, when I'm pointing that way, I have to learn that that's left. And when I'm pointing that way, I have to learn that that's right, even though for me it's the exact opposite. So every once in a while, we still get mixed up there. Courtney, thank you for correcting my mistake. And thank you for being nice to me when you did it. Okay, what's the polarity of this now? Which side of the magnet, this new electromagnet that was just formed, is this? What is it? That's the north, that's the south. Didn't we say magnetic field points from north to south, not south to north? The magnetic field outside of a magnet points from north to south. The magnetic field inside of a magnet is essentially like the domains, which point from south to north. So outside from north to south always, and that's almost always what we're looking at. But in this one particular case, these solenoids, we look at the magnetic field inside, and it's going to be opposite from south to north. Good? All right. Let's take a look at multiple choice number 66. I'll give you about 30 seconds to do that one, please. All right, let's take a look at it here now. We've got 4 diagrams. In all 4 diagrams, we have 2 magnets. Now, we're not given the polarity of those magnets, though. But we can tell by shapes whether there's attraction or repulsion, right? And if there's attraction, we know that we have to have opposite poles. If it's repulsion, we know that we have to have like poles. So, tell me, number 66, which magnetic fields indicate that the magnets will repel each other? Diagrams 1, 2, 3, or 4. Let's not even look at our options here. Okay, let's not try to look at combinations. Let's just look at each one of them on their own merits. Are they going to attract or repel in diagram number 1? It's going to attract, yeah. In fact, we could label the polarity of those if we wanted to. Don't have to, but could. This is going to be north. This is going to be south. It's going to attract because it's opposite poles. We know the left one is north, the right one is south because of the direction of the magnetic field there. All right, let's take a look at diagram 4. I think diagram 4 is the next easiest one to do. So let's look at that one. It looks a little bit more like the ones that we've looked at in class. Diagram 4 is going to attract or repel. That's a repulsive force, right? That's like poles pushing each other away. We know that that's going to be a north pole. That's going to be a north pole as well. We know that because the magnetic field goes away from the north. So that's going to repel. All right. Diagram 2 looks a little bit tougher. Do you think that's going to attract or repel? What makes you think it's going to repel? Okay. That's not actually the way that I was looking at it, but that's a good way to look at it as well. Eric said he can tell that this is going to be north, this is going to be south, and this is going to be north, and this is going to be south. So if we're bringing south near south and north near north, they're going to repel each other. Good. Okay, good. That's a good form of reasoning to use. They are going to repel each other. It's not, however, the form of reasoning that I was using. Anybody else have another form of reasoning to determine that that's going to be a repulsive force? Brendan? The lines don't join up. Right? If the lines aren't joining up, it's got to be a repulsive force. Okay, so we know that's going to be repulsive. Now, odds are number 3 is going to be attractive because each of our options only have 2 possibilities for repulsion. Why is it attractive? How do you know it's attractive? There's 2 ways. We can use Eric's logic here and say, this has got to be north, this has got to be south, this has got to be south, and this has got to be north. So north goes against south, south goes against north, it attracts. Or we can use Brenda's logic. The lines join up, so it's got to be an attractive force. So what's the answer here? 2 and 3 are repulsive forces. B is going to be the answer for number 66. Sorry, what is it? 2 and 4. Sorry, 2 and 4. Having trouble with directions, left and right. Having trouble with numbers as well, too. Well, they are Roman numerals. Come on. Give me a break. 2 and 4 here. Good? See how easy it is to make a stupid mistake? And you do the whole question right, and then you just circle the wrong one because, I don't know. I don't know why. Okay, let's take a look at this one, okay? Give you about 30 seconds to do this one as well. All right, let's take a look at this one now. 2 bar magnets of equal magnetic strength are placed as shown below. The point P is the same distance from each of the magnets. Now, be careful with this. Some people will look at this and say, oh, I see a dot. That means out of the page. They're not saying here this dot means out of the page. Okay? An X means into the page when we're indicating direction, and a dot means out of the page. But they're not trying to indicate any kind of direction here at point P. They're just saying, look, this is a point in space. Which way is the magnetic field acting at that point? Which way is it acting? Well, let's pretend magnet number 1 is the only magnet there right now. Okay, magnet number 2 isn't there. Which way does the magnetic field point because of the North Pole? Points away from north. Now, the entire magnetic field shape, it would be non-uniform, would go around like this, but we don't care about that. We only care about one point. So the magnetic field caused by that magnet at that point would be straight up. The magnetic field caused by number 2, if we pretend 1 isn't there, is going to be straight towards it. What's the combined magnetic field going to look like if we have one magnetic field that's up and one magnetic field that's to the right? Combine them, it's going to be up and to the right. What's the answer? D is the answer. Good? One more. Well, people, I don't know what it is about this one, but people don't like this question. I will clarify just a little bit before you do this one. Okay, these compasses are all, they're trying to show these compasses all pointing out of the page. But they're just trying to do it in a three-dimensional diagram. Okay, so they're all pointing this way, which is meant to be out of the page, the same direction in all 4 cases. Okay, see what you can do with that one over the next minute. Let's take a look at this one as well now. First thing we got to do here is recognize that it's really a Wiregrass Rule question, right? It's really a magnetic field caused by an electric current question, an Oersted question. We got electrons moving through the wire upwards. Okay, let's take a pen, use it as a manipulative, and determine what the direction of the magnetic field is. If that pen is pointing upwards, stick my left thumb, because it is electrons, my left thumb upwards, my magnetic field is going to go to the right, sorry, to the left, when my fingers are in front of the wire. My magnetic field is going to go into the page when it's to the left of the wire. My magnetic field is going to go to the right when my fingers are behind the wire. And my magnetic field is going to go out of the page when my fingers are to the right of the wire. A compass points in the direction of the magnetic field. Which compass is pointing in the correct direction, given what I just said here? Which one is it, Joel? 3? We said when my fingers were to the right of the wire, they were pointing out of the page. So the magnetic field has got to be out of the page. So number 3 is correct. Behind the wire, remember, my fingers are pointing to the right. That compass is not pointing to the right. It's not pointing in the direction of the magnetic field. In front of the wire, my fingers are pointing to the left. Okay, that compass is not pointing to the left. And to the left of the wire, my fingers are pointing into the page. That compass is not pointing into the page. So the answer is C. How many people got that one? Good, good. Call in question. Down, yeah. Yes, yes, yeah. If the electrons, the question was, if you didn't hear it, guys, the electron movement was downward, the current was down toward the bottom of the page, then we would stick our left thumb down, and everything would be the exact opposite. Okay, if you got a question, a little bit of a shortcut, if you happen to get this question, and then you happen to get another question very shortly thereafter that had a current going down the page, exactly opposite, you wouldn't even need to really do the hand rule, because you know that everything is going to be the exact opposite. Yeah, that's right. If you know one, you know the other. What a lot of people will do too is if you happen to get one question with a negative particle, and then you happen to see another question that's pretty much the same except it's a positive particle, same direction and so on, well, you know it's going to be the right hand. Some people will go through and do the right hand rule for it, and some people just say, well, look, I know it's going to be the exact opposite of what we just found. So if the direction is opposite or the charge is opposite, things are going to be flipped over. If it happened to be alpha particles going downward, then things would be exactly the same, because the direction would cause it to be reversed, the charge would cause it to be reversed, which would put it back to where it is. Good? All right, we had a little bit of homework last night. Let's take a look at that homework now on page 592. Let's take a look at these now. Which questions do we need to go over? 1 to 5, 6, 7, 8, and 10 to 16. Which of those ones do we need to go over? Yep. 15 and 16, yep. 14, 12, 12, 14, 15, 16. It looks like the later ones. Are those on like hand rules? Just weird stuff? All right, okay. 12, 14, 15, 16. Any others? Going once, going twice? All right. Number 12. That's a good question. What does dropping or heating a bar magnet decrease its magnetic properties? What is it that gives a bar magnet its magnetic properties? What's inside a bar magnet that gives its magnetic properties? What's different about a ferromagnetic material than a non-ferromagnetic material? Good. First of all, the ferromagnetic material has domains. Okay, the non-ferromagnetic material doesn't have domains. And if it's magnetized, then those domains are aligned. Well, what happens to those domains that are aligned as you drop it, or as you heat it, for that matter? They scatter, they kind of scramble. As you give kinetic energy to it, these domains have a tougher time staying aligned. What's one way to give kinetic energy to it? Drop it, bang it against the floor. What's another way? Heat it up. Okay, so what you do is scramble the domains. It decreases its magnetic properties. You drop it once, it's not going to cause it to not be magnetized, but it'll ever so slightly decrease its magnetic effect. Number 14. Explain why it is difficult to get an accurate bearing with magnetic compass near the poles. This is a great question. You know what? I know that some of you follow me on Twitter, and I retweeted something last night. I don't know if anybody saw that last night. It was perfect timing. It was absolute perfect timing. You guys know who Chris Hadfield is? He's the Canadian astronaut that's on the space station right now. He's the commander of the space station right now. He retweeted something, or he answered a question from somebody on Earth last night on Twitter, and I read it. And I retweeted it because it was perfect. It was about compasses. The question was essentially, do compasses work in the space station? And his answer was yes. Compasses work as normal in the space station. It's a weaker magnetic field, of course, okay, but they still work. It's still a strong magnetic field there, except at the poles. What happens to them at the poles? The compasses want to point down or up at the poles. Why don't normal compasses work very well at the poles? Because normal compasses, needles, can't point down or up. They have to point horizontally. Now, you need a special kind of compass, kind of a 3D compass, a compass needle that's in a liquid that allows it to point up or down in order to work at the poles. Does that make sense? So you're navigating in the North Pole. You better not bring your regular compass. Okay, you better bring another compass that is able to move up and down. Although, okay, I guess in the end, if it just spins around, because it can't go anywhere because it just spins around, right? I guess then you know that you're at the pole. You're either at the North Pole or the South Pole. And you're probably going to know which one you're at. Next one is number 15. Do magnetic field lines always run parallel to the surface of the Earth? Do they? The first answer to this question is pretty straightforward. Do they always run parallel to the Earth? No. They run more or less parallel to the Earth up here, okay, in mid-latitudes, but they're pretty much perpendicular almost to the Earth right here at the poles. So the answer is no. They don't always run parallel to the Earth. At the poles, they're almost perpendicular to the Earth. That's why we get northern lights and southern lights at the poles, because the magnetic fields are perpendicular to the Earth, as opposed to in the mid-latitudes, where the magnetic fields are parallel to the Earth, or virtually parallel to the Earth. And 16, finally, if a current-carrying wire is bent into a loop, why is the magnetic field stronger inside the loop than outside? That's a great question right there. That's probably the best question on the page. Why is the magnetic field strength stronger in a loop of wire right here than outside the loop of wire right there? Go ahead. Okay, kinda. Let's look at it this way. Go ahead. Yes, that's a good answer. There's a greater concentration of the field inside. It's kind of interference, right? This part of the wire generates a magnetic field right here, and it generates a magnetic field right here. This part of the wire generates a magnetic field here, and a magnetic field here. Right here has the magnetic field caused by this part and this part. Outside has the magnetic field generated by only one part of the wire. In the end, you got a whole bunch of different spots that all create a magnetic field in here, which end up creating a stronger magnetic field. But outside, each spot still has the magnetic field of only the one part of the wire that's causing it. Does that make sense? That's pretty much what Jordan said there. Good? Pardon me? Yeah. No, not so much. That's a good question. That's a very good question, actually, Colin. But the answer would be no to it. If you didn't hear that, his question, and I think tell me if I'm misunderstanding your question, but I think I've got it right. Colin said when magnetic field lines are closer together, it's a stronger field, right? And absolutely it is. Would that have anything to do with it here? It wouldn't, because the magnetic field caused by this wire right here, say 2 centimeters to the left of it, 2 centimeters to the right of it, it's going to be the same magnetic field. Okay. Now, if we get a magnetic field right here, a current right here, that causes another magnetic field here, 2 centimeters to the left, 2 centimeters to the right, it's the combination of these two magnetic fields really that's causing the stronger magnetic field. I guess you could argue that, you get more field lines, they're closer together. I suppose you could argue that. But in the end, it's more of a constructive interference type thing where lots of different field lines add up to give me a bigger field. Okay, first new thing for the day. It's another hand rule. We've learned 2 of them so far. The Wiregrass Rule that says you want to find the magnetic field caused by an electric current, stick your thumb in the direction of the current, fingers in the direction of the field. The Coil Rule says you want to find the polarity of a coil. Let's stick our fingers in the direction of the current, and our thumb will point in the direction of the field inside that coil. The hand rule for deflection works similar to, but yet a fair bit different from the other hand rules. It's used in a completely different scenario. Still talking about magnetic fields, but this time we're dealing with what we call an external magnetic field. A magnetic field that's already there. For instance, maybe you've got a charged particle that's moving down the page. It generates its own magnetic field. And we could figure out what the direction of the magnetic field caused by it was by using the Wiregrass Rule. But maybe you've got a couple of magnets over here. A north pole and a south pole over here. It has its own magnetic field. So now you've got a charged particle going through a magnetic field and generating a magnetic field at the same time. When that happens, you're going to cause a force. Whenever you have 2 fields, there's an interaction between the 2. There's going to be a force on this particle. Which way is the force on this particle going to be? Well, for that, to determine which way the force, not which way the field is, we can determine that by the Wiregrass Rule. Which way the force is, we're going to use the left-hand rule for deflection. It goes like this. Stick your thumb in the direction that the particle is moving. That's the same as the Wiregrass Rule, right? That's where the similarities end. Stick your thumb in the direction of the particle. So in this case, it would be down the page. This time, we're going to use our fingers still, but we're not going to bend them. Okay, we're going to keep them stretched out. Okay, straight. Thumb points in the direction of the particle. Fingers are going to point in the direction not of the field caused by the moving particle, like it was in the Wiregrass Rule, but my outstretched fingers are going to point in the direction of the external field. Okay, the field that's caused by these magnets. So thumb, fingers, the force is going to be the direction that your palm is pointing. So thumb, fingers, my palm is going to point which way? In this case, it's going to be into the page. It's kind of weird. Particles moving downward, magnetic field is to the right, the force is into the page. It's weird, but that's the way it works. Okay, all three of these things are always going to be perpendicular to each other. The particle is moving one way, the field is going to be perpendicular to that, and the force is going to be perpendicular to both of those. Now, it is possible, of course, to see a charged particle moving not perpendicular to the field, but we won't get any questions involving that. Can't use the hand rule for that, and we won't get any questions where we can't use the hand rule. When you write this down, you don't need to necessarily write the diagram down or draw the diagram. In the end, what you need to do is understand how this hand rule works. I'll write a little summary here. The thumb is going to point in the direction of the moving charge, just the same as it did with the Wiregrass Rule. My stretched out fingers, not my bent fingers, but my stretched out fingers are going to point in the direction of the external magnetic field. You guys know what I mean by that? The external magnetic field? The one that's not caused by the moving charge. There is one caused by the moving charge. We can find its direction by the Wiregrass Rule, the same as we did before. But that's not what we're trying to find here. My fingers this time are going to point in the direction of the external magnetic field. The palm of my hand is going to point in the direction of the magnetic force. So instead of just thumb fingers, like we had for the Wiregrass Rule and the Coil Rule, now we've got thumb fingers palm for the hand rule for deflection. What if we want to find the value of the magnetic force, how strong the magnetic force is? We could find the direction by the hand rule for deflection. The left-hand rule or the right-hand rule. By the way, when would we use the right-hand rule for deflection? That wasn't in the notes that you just wrote down. When would we use our right hand for that problem instead of our left hand? If it's a positive particle, right? Negative particle, left-hand rule for deflection. Positive particle, it's going to be the right-hand rule for deflection. Now we want to find the value of the force, the magnitude of the force, whether it's on a negative or a positive particle. We're going to use this equation. F is equal to QVB. F stands for the magnetic force, of course. And the units for that are going to be newtons, as it always is for force. What's Q stand for? What does the letter Q stand for there? This goes back to our last unit now. It's going to be the charge, right? And the units for the charge, of course, are going to be coulombs. If it happens to be a negative charge, we're going to drop the sign of the charge just like we did all of last unit. We never want to put a sign of a charge into an equation. B, that stands for the magnetic field strength, not the magnetic field that's caused by the moving charge. There is one there, but we don't care what its value is. This equation takes care of it for us. We want the value of the external magnetic field, the strength of the magnetic field that was already there. And it's going to be measured in Tesla. What do you think V stands for? Right? Yeah, it's the speed of the particle. This doesn't happen if the particle's not moving. If the particle's not moving, it doesn't generate a magnetic field. And if it doesn't generate a magnetic field, there's no force because there's no interaction between the external and the magnetic field that's not generated. No, I'll explain that in just a second. It's a V with an upside down T. And I'll explain what that means in a second. So the speed of the particle, and of course that's going to be in meters per second. Now, Courtney just asked a good question. Is this little thing right here an I? And I said, no, it's kind of an upside down T. What does this mean? It means that in order for this equation to be valid, the particle must be moving perpendicular to the magnetic field. The hand rule doesn't work if the charged particle isn't moving perpendicular to the field. The equation doesn't work if the charged particle isn't moving perpendicular to the field. So all of the questions that we will get will involve the charged particle moving perpendicular to the magnetic field so that we can use this equation. Or they will involve the charged particle moving parallel. If it's perpendicular, this is the force, and we can find its direction by the hand rule for deflection. If it's parallel, it's even easier. The force is 0. If the charged particle is moving in the same direction as the field, there is no force. If the charged particles are moving opposite to the field, there is no force. If it's perpendicular, that's the force. If it's something in between parallel and perpendicular, like 37.2 degrees, we're not going to learn how to do it. It's not that hard, actually, but we don't have to learn how to do it, so we won't. Let's do an example here. 12.1599 says an electron is traveling at 3.2 times 10 to the 5 meters per second perpendicular. That's good that it's perpendicular, because we know that we can't use our hand rule and we can't use the equation we just learned if it's not perpendicular. If it's parallel, we don't worry about that either, because if it's parallel, the force is 0 and there is no direction. If it's perpendicular, we can use the rule and the equation that we just learned. If it's something other than perpendicular or parallel, we can't do the question. It's perpendicular to this magnetic field. We want to find the value of the magnetic force. This is going to be speed. This is going to be the magnetic field. And we want to find the magnetic force. Let's get the magnitude of the force, and let's get the direction of the force. The magnitude is going to be found by the equation QVB. The charge is the charge of an electron, 1.6 times 10 to the minus 19 coulombs. Speed is 3.2 times 10 to the 5. And the magnetic field is 2.2 times 10 to the minus 1 Tesla. Let's multiply those together. 1.6 times 10 to the minus 19 times 3.2 times 10 to the minus 10 to the positive 5 times 2.2 times 10 to the minus 1. We get 1.13 times 10 to the minus 14, I think it was. 10 to the minus 14. So it's a pretty small value of force, but remember, we're dealing with a force on an electron, so it's a pretty light thing. It doesn't need a very big force in order to deflect it. Now let's determine the direction of that force. We've got a particle moving. There again, trying to do it in 3 dimensions here as opposed to the 2-dimensional way that I think is a bit easier, but this particle is going into the page. We've got a magnetic field going which way? Going to the right. How'd you know that? Yeah, the magnetic field goes from north to south. So we've got a charged particle going into the page. We've got a magnetic field, an external field going to the right. We're going to use the hand rule for deflection. Thumb in the direction of the particle into the page. Fingers in the direction of the field from north to south. Palm points upwards toward the top of the page. Make sense? Does that make sense, guys? Question? We don't have to know which way to point our palm. It's just going to automatically point in a certain direction, right? If I stick my thumb into the page and my fingers go from north to south to the right, then my palm automatically points up. Okay? I didn't know that when I started. It just worked out that way. Okay? Does that make sense, everyone? The hand rule, it's like the other hand rules in the sense that, you know, the other hand rules, you knew one thing. Usually you knew which way your finger pointed, and you wanted to see which way your, you knew which way your thumb pointed. You wanted to see which way your fingers pointed, and didn't have to know which way your fingers pointed. It just kind of worked out for you. This is similar, except that this time we're going to know 2 things. Okay, usually it's thumb, fingers, and we don't have to know which way our palm points. It's just going to work out for us. Every once in a while, you're going to know the direction of the force, and you'll have to kind of rearrange it and say, okay, palm, fingers, which way is my thumb point? But you never have to know that third one. It just kind of works out for you. All right, take a look at these ones on page 599, please, for the next few minutes. Actually, let's not take a look at question number 2. Why not? Why do I not want you to do question number 2? It's not perpendicular and it's not parallel. So question number 1 on page 599, please. Let's take a look at it now. Is there any way to find the direction of the magnetic force in this problem? Can we find the direction of the force? There is a force, and therefore there is a direction, but can we find it? We can't, because we don't know which way the particles are moving. Now, we know they're perpendicular, so we know the equation that we learned applies here, but we can't find the direction of the force because we don't know how they're perpendicular, left, right, up, down, whatever. This is a pretty straightforward question. We're just going to find the magnitude of the force by saying F is equal to QPB. Multiply the charge of the proton times the speed of the proton times the magnetic field strength. That should give us the answer that's in the book here, which is 2.35 times 10 to the minus 18. Good? Okay, one more example, and then we're going to wrap it up for the day, okay? 12.2 on page 600. Similar diagram, except this time we have a carbon ion. Carbon ion has a mass of 2.01 times 10 to the negative 20. Is that a 6? 10 to the minus 26 kilograms, I think. And a positive charge of 1.6 times 10 to the minus 19 coulombs. A positive charge. Now I'm going to circle that in red because I don't want to forget that I'm going to use my right hand when I do a hand roll. We want to find the speed at which the magnetic deflecting force will balance the gravitational force so that the carbon ion will travel in a straight line. So it's kind of interesting here. Gravity pulls it down, right? We know that gravity pulls it down. Presumably, the magnetic force must push it up in order to balance that out, so it's going to go undeflected. Let's just double check and make sure that the magnetic force is upwards. The positive particle is going into the page. The magnetic field is going from north to south. So my thumb points in, my fingers point towards the left, my palm points upwards. So sure enough, Courtney's doing twisty things with her arm there. But carefully, don't like tear something there as you're doing that. The magnetic force has got to be upwards here. So it's going to balance the force of gravity. We want to find the speed at which that happens. Let's say Fm, the magnitude of the magnetic force, is equal to the magnitude of the gravitational force. If they balance each other, then they've got to be equal. QPB is equal to mg. And let's solve for v. Anybody have their book open so they can see if that's a 5 or 6? I think it's a 6. But if somebody can check their phone or something there just to make sure. Is it a 6? Thank you. 10 to the minus 26 times 9.81 divided by the charge here of 1.6 times 10 to the minus 19. And the magnetic field strength of 6.32 times 10 to the minus 5. Okay, let's do this one on the calculator as well, just to make sure that you don't mess up on the order in which you enter these things here. Let's say 2.01 times 10 to the minus 26 times 9.81. Let's press equals there. Then let's divide it by some brackets. 1.6 times 10 to the minus 19 times 6.32 times 10 to the minus 5. Gives us 1.95 times 10 to the minus 2. Good? Had to do a little bit more with that one, right? We had to kind of think outside the box a little bit and go back to physics 20, balanced forces thing. All right, your homework for tonight was going to be worksheet number 11, but we'll leave it at page 600. The practice problems on page 600. So we'll just leave it at that, and we'll sign worksheet number 11 tomorrow night. Worksheet number 11, by the way, you can do. It will be assigned for Friday. So if you want to get a head start on it during scheduled help or whenever, then go ahead and do that. It's not due tomorrow, but it will be due for Friday. All right, that's it for today.